Hi, welcome to our 8th lecture, the Williamson ether synthesis. In 1540, Cordius showed that he could take ethanol with sulfuric acid and heat it to form diethyl ether. In 1851, Williamson expanded this methodology and took sodium ethoxide, reacted it with ethyl chloride, and formed diethyl ether. The Williamson ether synthesis is not limited just to aliphatic alcohols. You could also use aryl alcohols. Here we show phenyl with sodium hydroxide to form sodium phenoxide, which react with propyl bromide to form the desired product. The aliphatic alcohols require a strong base, such as potassium hydride, sodium hydride, LDA, lithium HMDS, to deprotonate because aliphatic alcohols have a pKa of around 16. With the aryl alcohols, a lower pKa leads to weaker bases being utilized, such as sodium ethoxide, potassium carbonate, cesium carbonate. The reason for that is the phenyl ring is electron withdrawing, and it pulls the electron density in, therefore lowering the pKa of your acidic proton. The solvents utilized are general polar aprotic solvents, such as DMF or DMSO. This avoids the dehydrohalogenation that leads to undesired side products. You can also utilize a phase transfer catalyst in this reaction. Hill showed you could take butanol, react it with sodium hydroxide, and form the sodium butoxide intermediate. With a phase transfer catalyst, such as tetrabutyl ammonium hydrogen sulfate, the tetrabutyl ammonium will bind to your alkoxide and pull it up into the organic layer, where your benzyl chloride or your alkyl halide can react via an SN2, yielding your desired product. So this is a nice way to take your polar alkoxides, pull them up in the DMSO layer, or up into the organic layer, to generate product. The mechanism for this reaction is fairly simple. Here we show sodium hydride as your base. The hydride deprotonates your aliphatic alcohol, releasing hydrogen gas, which will bubble off. Then you have your sodium ethoxide, which undergoes an SN2 reaction. This yields your desired diethyl ether. With the SN2 reaction, if you have secondary alkyl halides or such, you will observe the inversion of stereochemistry. The nucleophiles can be primary, secondary, tertiary, aryl, or heteroaromatic. The metal oxide intermediates can be stored under inert conditions. Alkyl, allylic, benzylic, and methyl halides give the highest yields. With polyhalide electrophiles, the reactivity favors the better leaving group. For example, if you have a alkyl halide with both a bromo and an iodo moiety, the reaction would favor the iodo because the iodo is a better leaving group. The reaction between lithium alkoxides and alkyl iodides proceeds via a single electron transfer. There are limitations to this, however. Sterically hindered alkyl halides undergo E2 elimination, especially when heat is applied. You can see this with very sterically hindered primary alkyl halides, but more commonly with secondary alkyl halides. Reaction does not work with tertiary alkyl halides because if you recall from sophomore organic, you cannot perform an SN2 due to the sterics on a tertiary center. Something to be aware of is both you can get C and O alkylation with alkali phenoxides. If you think a little bit about the mechanism, that negative charge on the oxygen can feed into your electron withdrawing ring, causing carbon-carbon bond formation.